Hello everyone, thank you for attending my presentation. I'm Qianping Zhang from the Chinese University of Hong Kong. In this presentation, I'm going to introduce our work, improving the transferability of adversarial samples by Path-Augmented method. Here is the overview of our paper. We first discovered current augmentation-based approaches such as SM suffer from limited and overlong augmentation passes. Then we propose Path-Augmented method PAM to solve the problems. In PAM, we first select representative path directions to construct a candidate augmentation path pool. Then we settle the employed augmentation passes during adversarial sample generation with greedy search. Furthermore, we train a semantic predictor, which is a lightweight neural network, to constrain the length of each augmentation path. Extensive experiments validate the superiority of our method over state-of-the-art baselines. DNNs are known to be vulnerable to adversarial attacks. We can generate adversarial examples to identify the deficiencies of DNNs. Transfer-based attacks have gained increasing interest recently due to their high threat in practice. Transfer-based attacks utilize white box attacks to attack a local surrogate model, and then directly transfer the resultant adversarial samples to the target model. There are generally two categories of attacks on improving transferability. One is the optimizer-based approaches, which adopt more advanced optimizers to escape from poor local optima during the generation of adversarial samples. The other is the augmentation-based methods, which resort to data augmentation and exploit multiple training images to learn a more transferable adversarial sample. Among the augmentation-based methods, DNN and TNN augment images via geometry transformation, while SIM and AdMix augment images along a linear path. However, existing augmentation approaches still have limited transferability. For example, the scale-invariant attack method, SIM, augments multiple scale copies of the target image. Such method only considers the image augmentation path to one baseline image. Besides, although it attempts to augment images that are semantics consistent to the target image, it fails to constrain the length of the image augmentation path, which may result in augmenting semantics inconsistent images. Therefore, we propose a transfer-based attack called Path-Augmented method, PAM. PAM proposes to augment images from multiple image augmentation paths and constrain the length of augmented paths to improve the transferability of the learned adversarial sample. The first step of augmentation path exploration is to build the augmentation path pool. To reduce the numerous searching space and align with SIM, we only consider the pure color images for the augmentation path. We divide RGB channel by 3 points, -1, 0, and 1, to largely diversify the paths, so we have 27 representative augmentation paths. The second step is to select the augmentation path in the path pool. We rank the 27 augmentation paths by deploying adversarial attack and measuring the average transferability on a development dataset. We follow a greedy manner in that we choose the top N augmentation paths and directly combine the gradient of augmented images from those augmentation paths together for generating adversarial samples. We train a semantic predictor SP to predict scaling factor of each augmentation path to constrain the length of the augmentation path and augment the images in the semantics consistent part. The training objective function is attached. In a nutshell, our PAM tries to solve two problems of the previous methods, the limited and overlong augmentation paths. We first augment images from multiple augmentation passes to explore other augmentation directions. Besides, we train a lightweight neural network semantic predictor to constrain the length of each augmentation path for providing a semantics consistent gradient. The attacking equation is as follows. We conduct experiments on the ImageNet dataset to validate the effectiveness of our method. We first attack both undefended and adversarially trained models. Our approach consistently outperforms the state-of-the-art baselines. We then combine our attack method with input transformation techniques. Our approach can also consistently outperform the state-of-the-art baselines. Finally, attack state-of-the-art advanced defense methods. We can also achieve SOTA performance. Example demonstrates the effectiveness of both augmentation path exploration and semantics predictor. The figure visualizes the original images and augmented images. We fail to identify the object in the augmented image of SNM, but we can recognize the object in SNM with semantic predictor. To sum up, in this work we propose PAM to augment images from multiple augmentation passes during the generation of adversarial samples. We also train a semantics predictor to constrain the length of each augmentation pass. We conduct extensive experiments to validate the superiority of our method over state-of-the-art baselines. Thank you for your listening.